This is the solution to number 7 on the AP current electricity problem set. We'll start by reading the problem. A series circuit consists of 3 identical lamps. That's actually key information in this problem. By anytime you in current electricity you hear the word identical, that devices are identical, what that means is that their resistances are the same. All the devices have the same resistance. Connected to a battery as shown in the diagram below, when a switch S is closed, what happens to, and then you have a bunch of questions to answer, which we'll get to. You have the diagram. What I would encourage you is to redraw the diagram. Any practice we can get on drawing circuit diagrams is good practice. So we're going to start there. And I'm going to start with a source of potential difference. The symbol often seen for potential difference is epsilon. Nonetheless, we'll come back and we'll label everything here when we're done. And as given in the drawing, you have 3 identical lamps. So we'll go 1, 2, and 3. And then we'll connect everything with wires. So we come down here, connect our entire circuit. We have a series circuit, but then what they do here, interesting in this problem, is we create a branch right here that has a switch. Let's label all our information. We've got our total voltage here. We've got lamps A, B, and C, which each have resistance R. Okay, so we're good there. And now that our circuit is drawn, let's go back up and take a look at this. When switch S is closed. All right, so I'm going to do this in red. So we close the switch. And of course, what that does is it allows current to flow. But what happens is, and this is unique in this question, by closing the switch, what you do is you're short-circuiting lamp C. So the current is going to take the path of least resistance. You've probably heard that expression before. And instead of splitting at this junction right here, like it normally would in a parallel circuit, it actually is going to flow through this wire, through lamps B and lamps A, and go back to the battery. So lamp C gets short-circuited. What that ultimately means is if lamps A, B, and C were on, which they were, because before we closed the switch, the current would have gone just through the one path, through C, then B, then A, and then back to the battery. Now what happens is you short circuit lamp C and lamp C turns off. Okay? What I would propose is that we not answer the questions in the order A, B, C, D, and E. I'm going to answer them in a different order because there's some things that we can learn from this information on short-circuiting lamp C. So the first thing I'm going to do is I'm going to answer D. By short-circuiting lamp C now gets no voltage. And we'll put in here as a reminder because of the short circuit. We know because the lamps are identical that the voltage that A uses up has to be equal to the voltage that B uses up. The question becomes, what happens to it? Does it remain the same? Does it increase, decrease, whatever the case may be? Okay, so as we take a look at this total voltage, because these were in series, was divided equally among the 3 devices in this case because the devices were identical. That means A would get 1/3 the total, B 1/3 the total, and C 1/3 the total. But what happens when we close the switch? Now C gets none. What does that do? That means the total is now divided by is used and divided up by just A and B. So, though the voltage in A and the voltage in B is the same, we know that it's going to go from having been 1/3 the total voltage to now each gets 1/2 the total voltage. So, from VT over 3 to VT over 2. Okay, so we have some answers there. Next easiest question, in my opinion, to answer is question C. If we take a look at, and what they're looking for is what happens to the total current in the circuit. The total current would be calculated by the total voltage divided by the total resistance. The Indian sees the vulture over the rabbit. Well, what happens to the total resistance? If lamp C is short-circuited, it's no longer part of the circuit. So the resistance goes from, okay, the total resistance goes from being a value of 3R. Remember the total resistance in series, you simply add them up. So that goes from 3R to 2R. So what happens to the total resistance? It goes down. The total voltage is not changing. So inverse relationship between total current and total resistance, so the total current increases. Okay? Next easiest question to answer is both A and B. B is the easiest to answer because the power in C is 0. No matter what two electrical quantities you want to use, you're left with no current and you're left with no voltage, so that would be 0. The important thing that you learn in this question, if you didn't already know it, is that the brightness of a bulb is directly proportional to the power it's using. We probably understand this intuitively because we know, for example, that a 60-watt bulb is not as bright as a 75-watt bulb, which is not as bright as a 100-watt bulb. Well, what do you hear? The higher the power number, the brighter the bulb. So a direct relationship between power and brightness. Well, with C, lamp C, getting no voltage or current, its brightness would be 0. So, we also know that since they're identical lamps, that the power that A uses and the power that B uses is the same. The question becomes, does it increase, decrease, or remain the same? Well, the answer is that it increases. Both bulbs will get brighter. Both will dissipate more power. The reason for this, if we take a look, and here's what I would encourage you, here's how you answer these brightness questions that are, of course, related to power. Select the power equation for which the electrical variable in that type of circuit remains constant. What I'm saying to you is, select a power equation, what kind of circuit, A and B are in series. What's the electrical variable that remains constant in series? And that's I. And that include the resistance. So select the power equation that includes resistance and the electrical variable that remains constant in that circuit. And in this case, that's I. Current remains constant in series. All right, so in the analysis of this equation, the resistance doesn't change for either lamp, A or B. What does change? The current. We just got done saying that the total current increases. Well, in series, they both get that current. So if the total current increases, so does the power. So the power in A equals the power in B, and they both go up. So they will both be brighter. And then finish it up to wrap it all together. Our answer to E is now easy because, as just said, power is directly proportional to intensity. Of course, another word for that is brightness. And there's your answer to number 7.